Hello, welcome to week 4 of process control. The first mini lecture this week, lecture 4 in your handout, is about systems with challenging dynamics. So before we move on to the next lectures, which are looking at actually how to start controlling a process, we're just going to take a look at a couple more examples of processes that don't behave in the standard first and second order ways that we've looked at. We've learned that a process has a transfer function and that the transfer function can be written like this, and the points at which these factors are 0 influences the dynamic response. The Laplace transform of each one would look like this, e to the a1t, and recall the points where these are 0, the poles of the system, and that occurs at s equals a1, a2 and so on. So if the real part of a1 is less than 0, then we're going to get a decay in our response, because this is going to be e to the minus something t, and that will decay to 0. So we'd say that's a stable response, it's a bounded response, it stays within certain limits and decays to 0. Conversely, if the real part of a1 is greater than 0, this is going to be a response that increases. So we'd say it was unstable, it's unbounded, because it doesn't stay within any limits. So we understand what stability is. We're going to see that there are occasions where you can have a steady state which isn't stable. Okay, so this is the example. It's a jacketed exothermic reactor. So you can see my sketch here. We have a reactor here, that's at temperature T. It's exothermic, so we need to be removing heat from that. So we have cooling water coming into a jacket surrounding the reactor. The cooling water is coming out again. That's at temperature Tc. And the cooling water temperature is not being significantly affected by the temperature of the reactor. So what's going to happen? We want to look at our process. Here's a plot of temperature against power. This is heat transfer or creation. So first of all, let's look at this blue line. The blue line shows us the rate of heat transfer out of the system due to the cooling jacket. So the cooling jacket is at temperature Tc and the reactor is at temperature T. So the rate of heat transfer is going to be proportional to T minus Tc. And so the bigger T, the bigger the rate of cooling, and that's linear. So we have a straight line to show the amount of heat that's being removed from the reactor. Our red line here, that shows the heat that's being generated by the reaction, and that's not linear. That has an S shape, as you can see. So operating a reactor like this, we're going to want to operate it at points where the heat being produced by the reaction is equal to the heat being removed by the jacket. That should be a steady state point that we can operate at successfully. And you can see there are 3 points like that, P1, P2 and P3, and all of those, the heat produced is equal to the heat removed. Where do we want to operate? Well, P1's down here. That's probably not a good point because it's not going to be very productive. It's cold, reaction rate is slow. Maybe you could operate at P3, but perhaps the temperature is too high to operate practically. Maybe there's chemical degradation or the materials of the equipment can't withstand that temperature. So let's say we want to operate at P2. Can we do that? What happens if we try to do it? Well, if you consider P2, let's consider that there's a disruption of the system which increases the temperature a little bit to a new T, a higher T. And if you look at that, you'll see that at this new point, the heat being produced by the reaction is greater than the heat being removed. And the effect of that will be to continue to increase the temperature of the reactor. It will continue to increase until we hit this point where again the temperature, the heat from the reaction is balanced with the heat removal. And conversely, if you are disrupting the system and reducing the temperature a little bit, then you find that the temperature produced by the reaction is less than that removed from the jacket by the jacket, and so again we continue to decrease until we hit the new steady state point. So we see that this is an unsteady point. Whilst it's a theoretical steady state, if you tried to operate there, you would find that any disruption to your process would make it flip to either P1 or P3. You can obviously check P3, is this stable? Well, yes, because if you have a slight perturbation which decreases the temperature, now we have more heat produced than removed, and that will tend to push it back towards P3. And if you have a slight increase in temperature, now the heat removed is greater than the heat produced, that will tend to push it back towards P3. So this is stable because of the process dynamics. This is unstable. So if we want to operate here, we're going to need a controller of some sort to try and make that a stable point. Looking at the transfer functions, we would know that the process can be described with a transfer function. At P1, the transfer function is going to be stable, so it would be of this form here. But at P2, it's unstable, so we'd have a -1 on the transfer function there. Likewise, at P3, it's stable again, and we have a +1. Now, this is just one process. How can it have 3 different transfer functions? That doesn't make sense. We'd use the same set of equations to describe the process in all 3 cases. The equations haven't changed. Why does the transfer function change? Well, that's because we have a non-linear function here. This S-shaped thing is non-linear, and that means that each time you want to model the process for control, we need to linearize it. The Laplace transform methods are only working for linear sets of equations. So at P3 or at P2 or at P1, you'd have to linearize your equations. And each time you linearize them, you get a different equation. So the linearized equations would lead to the transfer function here for P1, the linearized equations at P2 would lead to this transfer function, and so on. So that's why we can have 3 different transfer functions for the same process. Okay, so that's our first example of something a bit different happening. Our next example is called the inverse response system, and I'll show you that on the lecture handout notes that you've got. So this is an example we'll look at in the first place. This is a fire tube boiler. So it's a boiler where fuel's coming in, it's combusted in this large tube, and then the combustion gases come out and go through small tubes and out as flue gas, and that's to produce heat which will boil water in here. So water is continuously flowing in and boiling, and then steam is continuously produced out the top. What happens when there's a step change in the feed water rate here? There's a step increase in flow there. What would you expect to happen? Well, if more water is going in, I guess you might think that ultimately you'd have a new steady state with a higher water level than the old one. What we actually find is that there are 2 contributions to the output. The first one is a minor effect, and it tends to decrease the water level. The extra amount of cold water coming in drops the temperature in the boiler, and that causes a drop in the water level. And it's only after a little bit of time that then the amount of water that's flowed in has been enough to make the increase in water level due to the larger intake significant, and ultimately that becomes the major effect. So it's a type of process where we have 2 effects and they're counteracting. The minor effect is causing the water level to go down, the major effect is causing it to go up, and so they're going to be in competition in terms of their influence. So we could see that on these response plots. The minor effect makes it go down, but not very much, but it does it quickly. The major effect makes it go up quite a lot, but more slowly. And so when you add those together, and as a linear process, you can just add the 2 responses together to find the combined response, then you see it goes down and then up. And at this point here, the response is 0, is where it was before, and we'll come back to that point in a moment. Why are we interested in them? Well, they're an interesting case of something different that happens, and they're worth knowing about because it can avoid you getting misled. If you see a response which is starting to go one way, be aware that actually it could be something that ends up going the other way for its new steady state. And of course this is something that you could model more simply as a first order with a delay, and then that would take out the initial misleading response. Okay, so we can use this with our Laplace transform notation the major response has this case, simple first case example, with K1 and tau1, and the minor response has K2 and tau2. And the overall response is the major one minus the minor one, because they're counteracting. And you literally just take one away from the other to find the overall response. And then we've put them over a common denominator so that we can find the poles of this. So we can consider the conditions that are going to be necessary to get an inverse response. So the first thing that needs to be true is that the minor response needs to be faster than the major response. And that means that K2 over T2, or tau2, must be greater than K1 over tau1. So the inverse of the process time, that tells us how fast it is. The larger that number, the faster. And then we also involve the steady state gain, because a fast response with only a very small gain will have little effect on the process. So the parameter K2 over tau2 indicates the speed and significance of that response. So that happens faster than that one. And we can rewrite that by multiplying through by tau1 and K1, and it looks like this, the ratio of the time constants to the ratio of the gains. And then the other condition is that ultimately the major process is dominant, so that means that K1 must be greater than K2, because ultimately after a long time the major response has the higher steady state gain, and that dominates the response. Again, divide through by K2 and we get K1 is greater than K1 over K2 is greater than 1, and we can combine those two conditions then to see that tau1 over tau2 is greater than K1 over K2 is greater than 1. And when that's true, you'll have an inverse response. So you know what to look out for to get one. And we can also look at what that means. We had an observation a moment ago that the transfer function was interesting because it passes through the axis here. So we know that the response, ultimately, for example, when it reaches a steady state, we know that the output response is equal to the steady state gain multiplied by the magnitude of the input step function, if that's the input. So the magnitude of this response indicates the gain, and so if the magnitude is 0, as it is here, then that must mean the gain is 0 at that point. And that corresponds to the numerator of our transfer function being equal to 0. So we talked before about the poles of the transfer function, that's when the denominator is 0, and likewise we have a condition which we call zeros, and that's when the numerator is equal to 0. And so for this expression, you can see it's a first order expression of s. There's going to be one 0 associated with it, and if you calculate what that would be, 0 is when the top is a 0 is when the numerator is equal to 0, so we can find s to make that true, and you find this, that s is equal to K1 minus K2 divided by K2 tau1 minus K1 tau2. Rearrange it and it looks like this, and then we can see how that looks like with here. So K1 divided by K2 minus 1, well, K1 over K2 is greater than 1, so this is a positive term for the inverse function. Tau1 over tau2 minus K1 over K2, that's this term, take away this term, that's going to be positive. So that means that this is a positive number, and so that tells us, this condition with this observation tells us that if the 0 has a positive value of s, then we have an inverse function. So that's positive for an inverse function, and so we can consider how that would be plotted on the complex plane. And we know that this is the real numbers, real part of the number, imaginary part of the number. We've seen before that poles, which are plotted when you have two distinct real negative poles, that's what we have here, and those correspond to the two poles of these terms. And now we can plot a 0 as well. So poles are plotted as a cross, zeros are plotted as a circle, and when you have a positive 0 like this one, then that's indicative of an inverse system. So that's the sort of response you'd expect to get. And our third example is going to be for recycle systems. This is a more complicated example than the one we're going to look at, but it's a system where you have part of your stream heading back and then re-entering the process. We're going to look at a slightly simpler case where you have a first order process along with a recycle stream that has another first order process in it, and so you can plot that or sketch that out as we can see on the bottom here. So we have our input, we have our process, we have the stream coming out of the process, and then we're taking part of that stream, undergoes something new happening to it, and then it's added in to the input as well. So we have that loop. Each of these has a transfer function, and due to the linearity of Laplace transforms, we can take this and we can simply add the two things together here to get a function for what's coming out of it. So the objective is to create the transfer function for the overall system, given the individual components and its schematic. Can you do that? You might want to pause the video for a few minutes and try that yourself. See if you can take this system and follow it through, write out the equations to derive the overall transfer function. Okay, so now I'll show you how to do it. In black is the process we had, so I've considered, for example, a concentration coming in, a concentration coming out. We have C in coming in, and then we're going to have this stream added to it. So what's this stream? Well, that's coming from C out, so that's C out, which has gone through this process. So it's C out multiplied by KR over tau R S plus 1. That's what's coming out of the recycle stream, feeding in here, and they're being added together. So in this stream, we've got C in plus KR over tau R S plus 1 times C out. And then all of that goes through the main process here, coming out this way. And so this is going to be equal to this term here, C in plus KR tau R S over tau R S plus 1 times C out. All of that is then acted on by this process, so all of that is multiplied by K1 over tau 1S plus 1. And that's our expression for C out. Obviously we've got a C out here and a C out here. C out equals this. So we can rearrange this to find an expression for the transfer function, which is C out over C in. So that's what we want to find. We do that easily enough. We can group together the C out terms and then divide through the coefficient of those, and we get this expression here. We've got the K1 over tau 1S plus 1 term, which comes from these two parts, divided by this term, which comes from the C out minus this part multiplied by this part. So there we have a transfer function for the overall process, and we can rewrite that by multiplying through by tau R S plus 1 and tau R 1 S plus 1 to get an expression like this. So we can see that this is a second order process now from the denominator of that, and we can multiply it out in order to get it into a form we're more familiar with, where we've got an S squared term, an S term and the constant term. And we know that we can relate that to the overall system dynamics, because, for example, we know that the coefficient here is going to be related to the overall process time. We've got this here, so we want that to be a 1 for our standard form to work. So we need to divide through by that. So we have T1 TR divided by 1 minus KR K1, and that would be equal to tau squared, and so tau overall process time is equal to the square root of that. So we can see how a recycle stream can be implemented with the Laplace transform method, and we can get the overall process time out of that. So we notice a couple of things. We've got a square root, so we want what's in here to be positive. Obviously tau 1 tau r is positive. 1 minus kr k1, could that be negative? Well, if kr k1 is more than 1, what does that mean? The process is doing this loop, and K1 or Kr are the steady state gains. So if K1 times Kr is greater than 1, we're going to have an unstable process. It's probably impossible that it happens. It would keep on getting bigger and bigger and bigger because it keeps on going through both of them and getting multiplied. So Kr, K1 can't be greater than 1, so that makes sense. We have 1 minus that term, we have a real number here. But we do notice that if Kr, K1 does tend to 1, we're going to get a small number here in the denominator, and so our time constant can get very large. So with a recycle, with this condition, if the steady state gains of your process in the recycle start approaching 1, the whole process can become incredibly slow to respond to a perturbation. So that's another point to watch out for. That concludes this mini lecture, and the next lecture we'll start to look at how to implement some control. Thank you.